When we talk about the massive ocean weather systems controlling our world, El Niño usually gets the headlines. But there is a second climate engine operating right next door in the Indian Ocean that is just as massive. This is the Indian Ocean Dipole. You can picture it as a giant temperature seesaw stretching 10,000 kilometers between the coastline of East Africa and the shores of Indonesia and Australia. During normal years, that seesaw rests in a state of balance. But when the temperature on one side shifts, it reconfigures the distribution of heat and moisture across the entire basin. Understanding how this hidden system operates is the difference between viewing regional catastrophes as random events and seeing them as the result of a specific, trackable process. Let's look at what happens when this balance tilts into a negative phase. The water near Australia rapidly warming up, while the surface off the African coast plunges in temperature. This specific geographic tilt locks two opposing landmasses into simultaneous, yet entirely opposite, environmental conditions. This single oceanic shift effectively dictates where atmospheric moisture will concentrate and where it will vanish. The shift into a negative phase begins on the open water. Equatorial winds intensify, whipping across the ocean from west to east. These easterly trade winds act like a giant atmospheric snowplow. They grip the sun-heated top layer of the ocean, physically shoving it east. Millions of cubic kilometers of warm water begin to pool deeply around Indonesia and northern Australia. By moving this much heat across the globe, the system has physically relocated the engine that generates the world's rainfall. The coastlines of maritime Southeast Asia and Australia are home to millions of people who are now living directly underneath this displaced heat. That massive pool of warm water fuels intense, relentless cloud formation and atmospheric convection as moisture rises into the air. The resulting devastation includes above-average rainfall, widespread river flooding, and a heavily increased risk of tropical cyclones. The sheer speed and volume of this moisture frequently overwhelms local infrastructure and urban drainage systems. The eastern pole of the seesaw essentially becomes trapped under a dome of atmospheric moisture, literally drowning the region in the excess rain. Now, snap across the ocean to the arid landscapes of East Africa, where the atmospheric effects are entirely inverted. Because the warm water was pushed away, a vacuum is created along the African coast. Cold water from the deep ocean rises to the surface to fill it, a process called upwelling. This cold surface water prevents clouds from forming, choking the region of moisture and triggering severe, crop-destroying droughts. The exact same wind system that flooded Australia is actively starving East Africa of its life-sustaining rain. While the weather on land looks chaotic, the conditions that cause it are being tracked by precise scientific monitoring stations in the open ocean. The negative IOD is not a random weather event. It is a mechanical, trackable climate shift that follows a predictable cycle. Because the ocean takes time to move and change temperature, meteorologists can see these shifts early. This provides a window of 3 to 6 months before the peak impacts are felt on land. This critical lead time transforms a sudden catastrophe into a manageable logistical challenge. Survival depends entirely on applying the correct strategy to the correct hemisphere before the weather arrives. For those in Australia and Southeast Asia, the action plan involves elevating critical electrical systems and preparing waterproof emergency gear. It is also essential to store at least 72 hours of clean drinking water, as flash floods quickly contaminate local water grids. In East Africa, the priority shifts to the immediate requirement for rainwater harvesting and structural water storage to preserve what little moisture remains. Agriculture in these western zones must rapidly pivot away from traditional water-intensive planting and toward drought-resistant crops. We cannot stop the Indian Ocean's giant seesaw from swinging, but by understanding the mechanics of the negative IOD, we can build the resilience needed to survive the tilt.